The problem states that a curved bar is formed of a tube of 120 millimeters of outside diameter, meaning this one here that I have marked as D2, and 7.5 millimeter thickness. So this space here, this is 7.5 millimeters. The center line of this beam is a circular arc of radius 2025 millimeters. So this one here, I'm going to mark it at once. So this curvature is about 225 millimeters. Then it says a bending moment of 3 kilonewtons meter, and I'm going to write them down here. It says tending to increase the curvature. So if it's tending to increase the curvature, I'm going to put it like this and like this. And this is equal to 3 kilonewtons meter. It's applied, then calculate the maximum tensile and compressive stresses set up in the bar. All right, so for that, we need to consider a few things. First, I believe it's convenient to just write down the formula that we are going to use, and that formula is going to be, let's take the color, where should I put it? I'm going to put it like, yeah, right here. So stresses at any point of this cross section, like in here, like, yeah, something like this, it's going to be what? It's going to be moment divided by the area times the radius of curvature here, and then open brackets, there's going to be 1 plus radius of curvature of 2, then section constant like this, times then y divided by r plus y. Let me just write those y's more or less the same. So this is a times. Now, when they talk about the maximum tensile and compressive stresses, we know that maximum stresses are going to be located at the outer fibers or outer parts of the whole section. So they're going to be in point A and point B. And looking at the configuration we're having here, we know that at point A, because the moment tries to increase the curvature, this point is going to be in tension. I'm going to write it here. And this point here is going to be in compression. Like this. So we could use this formula to calculate both stresses in tension, stresses in compression, but I would need to consider kind of how to take the numbers across the section. And let's look at here, for example. So I'm going to have as a 0 here in where the central axis is, yeah, exactly in the middle. And this is going to extend from one extreme or one end to the other here. So at one point, I'm going to have one value that I'm going to use as y, and then another point, I'm going to have another value that I'm going to use as y there. So I'm going to put there, as this is in tension, I'm going to put it at 60 millimeters. And then here, I'm going to put it minus 60 millimeters. But why 60? Well, because the external diameter of this tube is 120 millimeters. So having that, this half is going to be this 60 millimeters, the radius of that. Then the values where I need to evaluate these stresses are going to be at, I'm going to write it here, at y equals 60 millimeters and y equals minus 60 millimeters. These are going to define my extreme points where maximum tensile and compressive stresses are going to be present respectively. So that one, the positive one, is going to give me the tensile stress, and the negative one is going to give me the compressive stress. So what we need to do here is to start finding each one of these elements. So the moment is given, what's the area, the radius of curvature is given, then the constant of the cross section, we need to calculate it. And here it presents a challenge because we do have a formula for round sections, but we don't have a formula for a tube in this, or constructed like this, like you have kind of an empty area in the middle. Yeah. So we need to apply a little bit of a similar approach we would do if we were trying to calculate the centroid of a figure, geometrical figure that is made of compound known areas, for example, triangles, squares, rectangles, all together. So we need to apply a similar principle there. It's pretty simple, and we're going to use it here. So first, let's start by calculating the easiest one, which are the areas, all right? So the areas in this case is going to be determined by what? Well, we have, let's see, to calculate the area, definitely of this ring, I would need to know the value of D1, all right? So I know that D2, let's put it outside, D2, well, let's give it a name, so area calculation. So we're going to have that the color. I know that D2 equals 120 millimeters. I know that the thickness is going to be equal to 7.5 millimeters, as given as data in the problem description. But then how much is D1? Well, easily D1 is going to be D2 minus 2 times T. So that's going to be equal to 120 millimeters. I'm going to use units here, but though I'm going to specify, maybe I'm not going to write units to keep the writing of the formulas short. And whenever I need to explain what units should go there and the changes, I will do it. But sometimes I won't use some units. But in this case, let me leave it there. So minus 2 times this 7.5 millimeters. And D1, the internal diameter of that tube, is going to be, let's go to the calculator, it's going to be 120 minus 2 times 7.5, and that's 105 millimeters. But as in the formula, as is stated, and I want to keep consistency with the values we're going to get, then I'm going to write this that it's equal to 0.105 meters. So we're going to start working in meters. Yeah? Hence, the area of this ring is very well known, and it's going to be what? It's going to be the pi divided by 4 of the square of the subtraction of the square of both areas. That is 0.12 meters, the outer diameter, minus 0.105 square, the inner diameter. And that's going to be equal to, let's put it here, so we're going to have pi divided by 4, and that times 0.12 square minus 0.015 square. And that is 0. Here, 0.020, 0.25 square meters. Perfect. This is a value I'm interested to keep track of. Awesome. Now, let's see, a bending moment. Well, bending moment is already given. You write it here like this, and that bending moment, M, is going to be this 3 kilonewtons meters, and this is going to be a positive moment. Why? Because this moment tries to increase this curvature. Yeah? So that's why we're taking it positive, because it tries to increase the curvature, meaning it makes it kind of more bended. Then let's calculate the value for the H2, or cross-section constant. Let me cross here section constant. Now this doesn't constant like this. And this cross-section constant is H2. And for a round section, a cross-section constant is defined as this value, like this, divided by 16, plus, then here is 1 divided by 128 times d to the power 4, divided by the radius of curvature, the square, and then plus some other high-order terms. And we are not going to write them, so it's not going to affect the accuracy of the result that much, because here what you have is the diameter to the power of 6, and then what it does is that just those higher order terms are very, very small. They amount to something, but we are going to truncate the series here, the expansion series up to here. Right? Now, the beautiful thing about this problem is that this radius that is given here is just served, meaning that it's already given to the central axis of the figure. Because this kind of part is like this area here. So here we have if I just draw it here, this is the circumferential, or the ring fitted there. So because this is a tube, it's like if I would have a 3D figure here, the tube continues like this. Yeah, but this is the cross-section constant for a round section, but we don't have the H2 constant, or the cross-section constant for a ring. So we need to treat this as what is called kind of as I mentioned, a compound figure of known areas, kind of when we're going to calculate the centroid of a complex figure. Yeah? So if I know that, just to put an example, that it's a figure is compound by, for example, a square here, and then it has also a semicircle here, for example. Let's imagine that this is a semicircle. Well, I don't know where is the centroid of this. I don't know where is the centroid of this. Then if I want to calculate the centroid of the compound image, so the whole thing, then there is a rule that we could follow using the areas and using the position of each one of those known areas, position of the centroid of each one of those areas. That's going to give me the centroid of the compound area, or the combined area. Now I'm going to remove this because I don't need it. This was just for the explanation. And what relates those two cross-section constants from the around cross-section of diameter D2 and around cross-section of diameter D1 is going to be this. It's going to be that the total area times this cross-section that I need is going to be equal to the largest area times the cross-section of that largest area minus the smallest area times the cross-section constant of the smaller area. So meaning that I could apply this formula to each one of these, kind of this big round and then this small round. Then using both areas, I can subtract them, that product, and then it would give me, I could kind of isolate this and get the value for it. Now let's then calculate all the parameters we need to determine the cross-section constant of my working geometry. Let's see, A1, for example, is going to be equal to pi 4, or pi divided by 4 times, actually I don't need big brackets here. This is going to be then the diameter 1, and that diameter 1 is going to be 0. How much? Yeah, 105 square, and that's going to be equal to, let's go to the calculator, and that's going to be pi divided by 4 times 0.15 to the square. Yeah, and that's 0.00866, let's call it 0.00866 square meters. And then area 2 is going to be equal to pi divided by 4 times the diameter of the outer part of the tube, and that's going to be 120, or meters, 0.1220 square. And let's go to the calculator. That's going to be pi divided by 4 times this square. Yes, and then we are going to write here that is 0.01131, let's call it, power of 2. Let me just fix a little bit this. This looks very weird. This one here. Awesome. Now let's calculate the cross-section of each one of those rounds. Let's call it rounds. So each section of a round cross-section equivalent, or with a diameter equivalent to D1, is going to be this much. So I'm going to have, right away, I'm going to apply the formula 0.5 square divided by 16 plus 1 divided by 128 times 0.105 power 4 divided by this radius to the central axis square, and it's going to be 0.225 square. And we said that we're not going to consider the higher order terms here because they are very small. It means that my value here is going to be, let's go to the calculator. I should at some point start calling this, for example, well, now it's not used anymore, but to assign variable names in GeoGebra, but it's okay. So we have, no, don't need this, 5 divided by 16 plus 1 divided by 128 times, here, this is to the power of 4 divided by 5, yes, that is square. And that's given me 0. How many zeros? 3 zeros. 1, 2, 3, 7. Yeah, 7078 0.078, and that's in square meters. But I could write that kind of, if I move the dot, the decimal point here, kind of 4 values to the right, I could write like 7.078 times 10 to the power of minus 4, because I moved the decimal point here, then square meter. Then for h, the cross section constant for the big round or a section with a diameter equivalent to d2, that's going to be, again, the 0 point application of the formula, square divided by 16 plus 1 divided by 128 times, again, that diameter, all of this doesn't look good, power of 4, divided by that, the radius, r. This is 0.225 square. And how much is that? Let's go to the calculator. And we are having, we call this E. Can I call it, for example, H1? Maybe. Let me just try so I can yeah. Then H2, I'm going to call that equal to 0.12 square divided by 16 plus 1 divided by 128 times 0.12 to the power of 4, yeah, divided by 0.25 to the power of 2. And then this is, I can apply these, these have 3 zeros, so I can write this as 9.32 times 10 to the power of minus 4 square meters. Then I'm going to just mark that this is one of the values I need, and this is the other value I need. Then to continue in this line, because I just want to make it smaller, how to extract it, yeah. Here I'm just trying to squeeze it here. So it means that the value I need, that is going to be using this equation here. So just to write it so we can have it at hand. So this means that this H2 is going to be equal to A2, this constant, minus this one, this constant, divided by A. So if this is the case, then I'm going to, I have the chance to do it right away because it's just substitution of values. So it's going to be A2, and A2 is this D, this one that I have here, just follow with me on, well, times H2, this much, yes, minus A1, and A1 is 0.08, which is equivalent to what I have in the memory of the calculator to C, times H1 here, and that's divided by the area, and the area was this one here, that was this value here, so it's B. And how much is that? Is 0.0, so I can write it down as 1, let me just change colors here, is 1.123, meaning 6 times 10 to the power of minus 3 square meters. These are the units of this, and this is what we got as a value. And actually I should mark them together to say that, hey, the values I'm going to need for my formula are which one? Well, actually I can extract them here. Values here needed, which are R equals to this 0.225 meters. Then area we said that is, I can write 2.65 times 10 to the power of minus 3 square meters. Then we have the moment. We said it was going to be this 3 kilonewtons, and that's going to give me then in megapascals maybe. Let's see, 3 kilonewtons meter. Then what else we need? We need H2 that we just calculated. It is 1.66 times 10 power of minus 3 square meter. And then we said that y for A is going to be 60, actually let's write like this, 0.6, no, 10 more, 6 meters, and then the y that I need to use for B is going to be equal to minus 0.06 meters. Then I have all the values needed to apply this formula here. Let me clean this up a little bit because we're going to use it. No, let me do something here. So I'm going to call this the area. Oh, no, it's going to be a mess. No, okay, let's just keep going like this, and that's it. So we have, so just keep track of this because yeah, I think I'm going to need, let me just change it at once because this is something that it was kind of bothering me. But it's 3 times to the power of 3 watt newtons meter. Awesome. Now we can calculate values. Maximum stresses. Here. Maximum stresses. So let's calculate the stresses at A. Now, by the way, I kind of assume because of the configuration of the problem that this is the value needed for A and this is the value needed for B, as I mentioned here. Might be that I got it the other way around, but you would understand that if the stress that's giving you is negative, then it belongs to this point because it's in compression, and if it gives you positive, it belongs to this point because it's in tension. So as easy as that. Then, so let's take for the first one. And then this is for A, yeah. Then the one in tension is going to be, well, a lot of things. How to do it, because it's not worth it if I just, what I can do is take this bunch of things and then move them here. And then I just come to write because I'm going to use the calculator for this, so it's just substitution of things. Let me see how it's more convenient. Yeah, so for A, so we are going to evaluate at y equals 0.06 meters. So not to make this video long, but you get the idea that we just need to substitute the value. Then this sigma A is going to be equal to how much? Let's go to the calculator once. So first, we're going to have that we need the moment, and that's why I wanted to write the variables here. Okay, so I don't repeat myself several times. So 3 times 10 to the power of 3, that's going to be divided by the area. The area is this much. Here is B times R, and R is 0.2025. By the way, what I'm using here when I write, for example, B here, I'm just referring or calling what the value that is stored in the memory of the calculator. And this is for the area. So instead of writing the whole number, what I'm doing is just calling the function that the calculator used to store this number. That's it. And you can give it variable names. I should have done that in the beginning, so it would be much easier. But then, our times, it's going to be this. 1 plus then R squared divided by H squared. And we said that H squared was going to be this value here. So we take it, yeah, I think it took it. I hope it didn't confuse it with the natural constant. Look at it, yeah. Then this times, we're going to have 60 millimeters. I said that that's going to be 0.8 divided in 5, yeah, plus 0.06. And that's giving me 1, 2, 3, 1, 2, 3. Perfect. That's giving me, I don't know why I let's delete this equals to 37. Actually, I could call it 0.24, yeah, meganewtons per square meter. And it's positive, and this is in tension. It's right here, tension. This is a tensile stress. Now for the stress at B, I'm going to evaluate it at minus 0.06 meters. And that's going to be equal to what? Well, I'm going to write it again. So it's going to be m, that's 3 times 10 to the power of 3 divided by b, which was the area, times the radius of curvature that they have, times 1 plus 0.25 to the 5 power of 2 divided by the cross-section constant that is stored in the calculator as E, then times minus 0.06 divided by radius curvature. Plus minus is minus, so this much. And look at this, giving me a negative numbers also in the order of the meganewtons per square meter. So this is giving me minus 50.61 meganewtons divided by square meters. And this is in compression. And here we have the answer that they were asking in the description of the problem. So we have tension and compression. And now we know for this case that stresses at P are going to be higher. They're going to be in compression, but they're going to be higher than the one at A that are going to be in tension. Look at the difference. 37 meganewtons in tension, 50 meganewtons in compression. So depending on the material you're using for this tube, then it's going to be good or bad, because remember that some materials, they work better under tensile stresses than compressive stresses. So it depends on that. Now to recapitulate a little bit, first we determined certain parameters that were not given, for example, the internal diameter here of the inner of the tube, and we needed that to calculate the area of this ring. So this is a ring. Then we went to see, okay, how much was the bending moment, and we said that it was going to be positive because it increases the curvature. When I say that it increases the curvature, means that this is going to be more bended. Then we went off to calculate the cross-section constant, and we don't have a value for this. Yeah, we don't have a formula for the cross-section constant, at least at hand, the cross-section constant for a ring. So what we did, we approached a similar case when we tried to calculate the centroid of a compound figure. So by joining or using the information of the centroid of the individual figures that make up this compound figure. So in this case, it's like this. To calculate the cross-section constant of this ring, then what I have to do is just to isolate the term and determine each one of these components. Areas of the outer round, let's call it like that, then area of the inner round, and then the respective cross-section constant of each one of those figures. So those are done in here, and then this is the resulting value that I need to use in my big formula here to calculate stresses or maximum stresses. Then what I did here was kind of a recapitulation of what are the values that I got and that I need to use in this formula. So I have them at hand. And then to evaluate the stresses, for example, at point A, that I know that's going to be in tension, I just use that, you know what, if the central axis is my 0, then you know that Y that I'm going to use in this formula is going to vary from 60 millimeters to minus 60 millimeters. And then I just evaluated this formula at 60 millimeters or 0.06 meters, which gave me this value of maximum tension stress. And then I evaluated this formula at minus 0.6 meters, which gave me this value of compressive stress. And this is the end of the problem. It's pretty straightforward. It's just the application of formulas. If you have any doubt or question, please leave it to me in the comments.